Okay. So I have in my notes that we did example 1 on Monday, right? That's where we ended it. Everybody in agreement? Okay. So let's take a look at example 2. In example 2, we're given a bacteria culture starts with 500 bacteria and 5 hours later has 4,000 bacteria. In A, you gotta find an expression for the number of bacteria after T hours. So our math model, sub the form, okay? And this is exponential growth, okay? Because the quantity is increasing over time, right? The number of bacteria is increasing over time. Our math model is A of T is equal to A sub 0 times Z to the KT power. That's our exponential growth model. All right, so A sub 0, right, from Monday is the initial quantity of a population or a substance. And so in this case, right, A sub 0 is 500 bacteria. So we put 500 in for A sub 0. Do our model, and we have A of T is equal to 500 times E raised to the KT power. And so now we got to find the growth rate K. Well, we know after 5 hours, the number of bacteria after 5 hours at T equals 5 is equal to 4,000. And if I put 5 in for T in our model, we have A of 5 is equal to 500 times E to the K times 5 power, or I prefer to write it as 5 times K. So A of 5 is equal to 500 times E to the 5K power. And so now, right, we can just replace A of 5 here with 4,000, and then we'll have one equation and one unknown, and we'll solve for K. So I replace A of 5 here with 4,000. And so we have 4,000 is equal to 500 times E to the 5K power. And now we have to solve for K. Well, this on the right is 500 times E to the 5K power. And so you know division undoes multiplication. So we divide both sides by 500 on the left. Left side equals 8, right? 4,000 divided by 500 is 8. 500 cancels in the numerator and denominator, and we're left with E raised to the 5K power. We're solving for K, and K is in the exponent on the number E, right? So how do we get rid of the E? ln, right? Take the natural log of both sides. We have the natural log of 8 is equal to the natural log of E to the 5K power. Right? So we take natural log of both sides. And so, property of the natural log function says the right hand side is just equal to the exponent of 5K. And now we can divide both sides by 5, solve for K. And when I switch to two sides, I get the decay rate K is equal to the natural log of 8 divided by 5. Well, using your calculator, I hope you got your scientific calculators. All right, get them out. I encourage you to get them out. All right, learn how to use the natural log function on your calculator. Right, don't trust me. I can make mistakes, you know that. Okay. And so, using your calculator, take the natural log of 8, and you should get a number in your display along the lines of 2.07944. Leave that number in the display and divide it by 5. Then you should get a decimal to 4 decimal places of 0.4159. Okay? Anybody get something different? So now we can put 0.4159 in for K over here. Okay? And then we'll have the exponential growth model for this problem. So when we do that, we have A of t is equal to the initial quantity, 500, times z raised to 0.41592 power. That is the answer to A. A says find the expression for the number of bacteria after T hours. Yes, sir.
Yeah, I'm assuming we have like more problems like this. Would it be wrong to, or is it accept the answer if we left K as like natural log of 8 over 5, or is it going to want us to put it in decimal form when we submit it?
No, well, the problems that I picked, 5 of them you're going to be using your calculator. Okay? The 6th one is just what you said. The 6th one you have to put natural log 8 over 5 in. Okay? So WebAssign, you never know which one they're going to want. Okay? Alright. That's a very good question. Alright, in B, find the number of bacteria that will be present after 6 hours. Well, to find the number of bacteria that will be present after 6 hours, we just put 6 in for T, right? We evaluate this function at T equals 6. And so we have A of 6 is equal to 500 times E raised to the 0.4159 times 6 power. And now, right, it's PEMDAS. Gotta simplify the exponent and then do exponentiation before multiplication. So the exponent simplifies to 2.4954. Exponentiation before multiplication, right? So you gotta take the number E. You should have an e to the x key on your calculator. Using that key, take E and raise it to the 2.4954 power. And I did not write down that number, but leave that value in your display and then multiply it by 500 and you should get 6,063. Now since we're counting bacteria, I rounded to the nearest whole number. Okay. Anybody get something different? You know, when I watch myself on video, I notice I stand up here a lot playing with the chalk. Makes me look like I'm come down with Parkinson's disease or something. Alright, in C, when will the population reach 15,000? Okay, so we want to know when will the number of bacteria reach 15,000, right? That's a time problem. So we replace A of T on the left with 15,000 and then solve for T. So we have 15,000 is equal to 500 times E raised to the 0.4159 T power. Solve for T. So, again, this is 500 times the number E raised to that power. So, division undoes multiplication. So 15,000 divided by 500 is 30. On the right hand side, right, 500 cancels in the numerator and denominator, and we're left with E raised to 0.4159 T power. And now again, T is in the exponent of number E, so to isolate T on the right hand side, we got to take the natural log of both sides. So we have the natural log of 30 on the left. It's equal to the natural log of E raised to the 0.4159 T power. And now on the right hand side is just equal to this exponent, 0.4159 T. So we have the natural log of 30 is equal to 0.4159 times T. And now you divide both sides by 0.4159. When I switch the two sides, we have the natural log of 30 divided by 0.4159. Right, so you just use the ln key, right, on your calculator. Take the natural log of 30, hit enter, leave whatever that number value is in your display, and then divide it by 0.4159. And I got the value of T, rounding to the first decimal place, 8.2 hours. So it's going to take 8.2 hours for the population of bacteria to go from 500 to 15,000. Okay. Anybody get anything different? Okay. All right, so flip over to page 2. And we'll do a problem involving half-life, which we discussed on Monday. Remember, half-life is the time it takes for a substance to be cut in half, right, to decay in half. The half-life of a radioactive element is the time required for half of the radioactive nuclei present in a sample to decay. So our model, instead of being an exponential growth model, it's an exponential decay model. K, instead of being greater than 0, is now less than 0. It's the decay rate. So in example 3, we're given carbon-14, one of the 3 isotopes of carbon, has a half-life of 5,730 years. So if you have a pound of carbon-14, it's going to take 5,730 years for it to decay from 1 pound to a half a pound. If 10 grams were present originally, how much would be left after 2,000 years? So on Monday, we talked about the half-life of a substance. Capital T is the half-life. And when we solve for the half-life in our exponential decay model, right? We got the half-life capital T. This should be on page 4, the back page of your notes, right? If you were here Monday. Is equal to, one way to write it is the natural log of 0.5 decay rate K. Okay? So this is the half-life. Okay? Well, we're given the half-life is 5,730 years for this problem. So we put in 5,730 for capital T. And now we can solve for the decay rate K, right? Multiply both sides of the equation by K. We have 5,730 times K is the natural log of 0.5. And now we divide both sides by 5,730. And we get the decay rate K is equal to the natural log of 0.5 divided by 5,730. That as a decimal is equal to, well, the natural log of 0.5 is equal to minus 0.69314781 divided by 5,730. And now when you divide the numerator by the denominator, this is one problem where you got to write out the decay rate to several decimal places. I get minus 0.000012097. So that is the decay rate for this problem. For carbon-14, okay? We are given that the initial amount of carbon-14 is 10 grams. So plugging in to our model, our exponential decay model, we plug in 10 for a sub 0, and that this long decimal for K. And we have our exponential decay model for this problem. Oops, I forgot the T. Right. So it's 10 times E raised to this value of K times T. Right, that's our exponential decay model for carbon-14. So in A, if if 10 grams were present originally, how much will be left after 2,000 years? Well, to find how much will be left after 2,000 years, we put in 2,000 in for t. So we have A of 2,000 is equal to 10 times E raised to the minus 0.0001297 times 2,000. And when I multiply our decay rate times 2,000, I get minus 0.24194. And so then when I raise the number e to this power, I get 0.785. Yeah, 0.785. And when I multiply that by 10, I get 7.85. 7.85 what? Grams. So we started with 10 grams of carbon-14, and after 2,000 years, the initial 10 grams will have decayed to 7.85 grams. Okay? Anybody get anything different? In B, it asks when will there be 2 grams left? So, where's our model? Right here. So it's asking, right, for what value of T is the amount equal to 2 grams? So we replace A of T with 2, and we solve for T. So in B, replace A of T with 2 on the left side, and then we solve for T. And so again, division undoes multiplication. So we divide both sides by 10. 2 divided by 10 is 0.2. 10's cancel on the right. And we're left with e raised to the minus 0.000012097 times t power. And now when you take the natural log of both sides, you have the natural log of 0.2 on the left. And when you take the natural log on the right-hand side, the right-hand side just equals the exponent. Minus 0.0001297t. And so, solve for t. Take the natural log of 0.2 and you divide it by this decimal, and you get the value of t. Anybody get an answer? Raise your hand if you got an answer for t. Miss Deal.
13,304 years.
Yep. So I actually went to one decimal place, rounded to the first decimal place, right? What you do is 13,304 and 13,304.4 aren't significantly different. Okay. That's a long time. What do you think you'll be doing in 13,304 years? Yes, sir.
So you say you divide the natural log of 0.2? Or you...
Yeah, so we divide both sides by this decimal,
Oh, yeah.
and so you get t is equal to the natural log of 0.2 times minus 0.0001209 And that is equal, when you do that division, you get 13,304 years. Okay? Alright. Any questions on that? Okay. So examples 4. Five and 6 are all on video. Okay? And so I came in early and made the video this morning. I've already uploaded it, but I gotta post a link on Oaks. Okay? And I'll post the link over the noon hour. Okay? I'll probably shoot you an email. So this homework is due tomorrow. 6 problems. Okay? So I kept it short. Alright, so that ends chapter 5. So now we move on, we actually go backwards to chapter 4. I'm going to start trigonometry. You think Kelly one, please? Alright. I'm curious about one thing. Is there anybody in here who didn't have any trigonometry in high school?
I did not, I don't think.
You've never had any trigonometry whatsoever? Cosine, sine, tangent,
Sounds familiar, a little bit.
Pythagorean theorem,
Yes.
a squared plus b squared equals c squared.
There you go.
So you probably got a little bit. Okay. Alright. So this first part, section 4.1, is a lot of definitions and so forth. Okay. So in 4.1 we talk about angles and how we measure them. Okay. So an angle is formed by two half rays, which have a common endpoint. So here's a half ray, here's a half ray, right? And we join them together at their endpoint, and that endpoint is called the vertex. And the size of the angle is the amount of rotation from, right, one side's labeled the initial side, the other is called the terminal side. And the size of the angle, right, can be thought of as the amount of rotation from the initial side to the terminal side. Okay. If we take this angle or one similar to it and draw it in the coordinate plane. We put the vertex at the origin, the initial side along the positive x-axis. We say then that the angle is in standard position. And we'll be drawing a lot of angles this semester in standard position. Okay? And so you can see, again, right, the size of the angle can be thought of as the amount of rotation from the initial side to the terminal side. Okay. All right, so there are two different ways to measure the size of an angle. The first is called the degree measure. And so you should be familiar with the idea that there is 360 degrees in one complete revolution. The degree measure of an angle is based on the assignment of 360 degrees to the angle formed by one complete counterclockwise rotation. So here we have in standard position, right, remember the vertex is at the origin, the initial sides are along the positive x-axis, and if we rotate it one complete revolution, right, that's 360 degrees. If we rotate in a counterclockwise direction, the measure of the angle is positive, and if we rotate in a clockwise direction, the measure of the angle is negative. So you can see here, right, the terminal side is along the positive y-axis. That's 1/4 of a revolution in the counterclockwise direction, and so that's a 90-degree angle. And it's positive because we're going counterclockwise. If we rotate the initial side in a clockwise direction to the y-axis, that's minus 3/4 of a revolution, and that makes the angle minus 270 degrees. Okay? So what direction you're doing the rotation determines whether the angle is positive or negative. Okay? All right. When two angles in standard position have the same terminal side, we say they are coterminal. So if we had drawn these two angles, 90 degrees and minus 270, in the same coordinate plane, they both would have their terminal side on the y-axis, and so we say 90 degrees and minus 270 degrees are coterminal angles because they share the same terminal side. Okay? The angles aren't the same size, they're just coterminal. So it says, are any two coterminal angles have degree measures that differ by an integer multiple of 360 degrees. So in the angles above, right now you said 90 and minus 270 are coterminal angles, because if you notice, if you take the 90-degree angle and you subtract 360 degrees from it, you get the angle minus 270 degrees. Similarly, if you take the angle minus 270 degrees and add 360 degrees to it, you get the angle 90 degrees. Okay? So that's what it means. Any two coterminal angles have degree measures that differ by an integer multiple of 360 degrees. Okay? So in this general example here, we have three angles, right? Here's the initial side, here's the terminal side, here's the angle theta, here's the angle, the spiral. It tells you how many times you go around. So here with this spiral, we go all the way around, 360 degrees, plus another theta degrees. And theta plus 360 have the same terminal side. So they're coterminal. And then if we do the rotation in the clockwise direction, from the positive axis to the terminal side, that's the angle theta minus 360 degrees. So all three of these angles are coterminal, okay? Because they all have the same terminal side. So theta plus 360, and theta minus 360 are coterminal angles. So in the exercise at the bottom of the page, for a 400-degree angle, locate the terminal side and sketch the angle. Find a coterminal angle between 0 and 360 degrees. Find a coterminal angle between minus 360 and 0 degrees. So 40 degrees is going to be less than 90 degrees, right? So the terminal side from angle 40 degrees is going to be somewhere between the positive x-axis and the positive y-axis. So let's draw that angle. Here's the coordinate plane. And so 40 degrees, right? Here's the terminal side. The angle 40 degrees, right? It's going to look something like that. Excuse me. I meant 400 degrees, right? It's 400 degrees that we got to draw. I apologize. Well, 400 degrees is equal to 40 degrees plus 360 degrees, right? And 360 degrees is one complete revolution. So I've drawn the terminal side in the correct place. So to draw the angle 400 degrees, we go 40 degrees in a counterclockwise direction, right? And then we go one complete revolution after that. And we end up right back here at this location. Okay. So first I drew the angle 40, went 40 degrees, and then one complete revolution. Right? That's what the spiral is telling me. And so this is the angle 400 degrees. Find a coterminal angle between 0 and 360. Well, to find a coterminal angle between 0 and 360, take the initial angle 400 degrees, and I subtract 360 degrees. And that gives me the angle 40 degrees. So the angle between the positive x-axis and the terminal side, from here to here, that's 40 degrees. So 40 degrees and 400 degrees share the same terminal side. In C, you gotta find a coterminal angle between minus 360 degrees and 0 degrees. So to do that, there's a couple of different ways to do it. First, you can subtract 360, right? That's one revolution in the clockwise direction from 400, and you know that'll equal 40 degrees. But it's got to be between minus 360 and 0. So we subtract another 360 degrees. That's two revolutions. Okay? So we subtract two full revolutions from 400 degrees, and we get the angle minus 320 degrees. So the angle's 440 degrees and minus 320 degrees are coterminal angles. They all share the same terminal side. Okay? Any questions on that? All right. The second way of measuring an angle is using what's called radian measure. And radian measure is based upon the arc length, the length of an arc. So here we have an angle theta in standard position, right? Vertex is at the origin, the initial side is along the positive x-axis, and this is the terminal side. And this is a circle. Remember, we studied the equation of a circle. This is a circle with its center at the origin, and it has a radius of r, right? The distance from the center to any point on the circle is r units. So if you have an angle that creates an arc between the initial side and the terminal side of r units equal to the radius of the circle, then that angle theta is equal to 1 radian. You guys have seen me wear my shirt, the red shirt? That's what it has on there, right? A circle, radius r, with an angle theta, and the arc length of the arc between the two sides of the angle is r units, and so that angle theta is equal to 1 radian. Okay, so degrees and radians are related, but how the angles are derived is a little bit different. Right? Degrees is based on rotation with 360 degrees in one full rotation. Radians is based upon the length of the arc between the initial side and the terminal side. Okay. So they're related, but how the angles are defined is a little different. Okay. So the circumference from high school, you probably remember the circumference of a circle of radius r is 2 pi r, right? That's the distance around the circle, right? The perimeter. And so it follows that the number of radians in one complete rotation of the initial side of theta equals 2 pi radians. Okay? All right. Let's go ahead and pause. Stop right here for today. And we'll pick it up here first thing tomorrow. Okay? So don't forget about the quiz tomorrow.